If you remember on Monday, we took a couple remedial baby steps to make sure we were ready for electrochem, including looking at redox reactions and half reactions. Then we ended the lecture period by taking our first glance at cell potential, which is calculations for E. We've got systems where E is positive, spontaneous, it'll automatically happen. And we have systems where E is negative, meaning it is not thermodynamically favored, and the reaction won't run on its own. What we're going to do with these next two lectures is we're going to spend today looking at thermodynamically favored reactions, and then we'll end the unit by looking at what happens when they are not spontaneous. So our focus today then is going to be what are called Voltaic cells. Some textbooks and professors will call them galvanic cells, which is the exact same thing. But really, we are looking at the general form of batteries. Now, batteries come in a lot of different forms, so I don't want you to think that the images that we're about to focus on is what it always looks like. There's lots of different types of batteries. But overall, Voltaic cells have a positive E because they are thermodynamically favored, and they can make things happen electrochemically. So that's what we're going to be looking at. Now, when I say looking at it, though, we're not going over as much theory as we are drawing today. We haven't drawn pictures together in a while. The last time we did a lot of it was Vesper. But what we're going to be doing is drawing our Voltaic cells and looking at all the electrochem that's happening to cause these batteries to work, to make the E be positive, and reactions are automatically taking place. Now, a basic drawing of our Voltaic cells is provided for you, but really on AP, there's going to definitely be a question that shows up. It'll either be a multiple choice question where they show you a battery and they'll point an arrow somewhere and you'll have to pick what is happening at that spot. Or it'll be an FRQ where you'll truly have to draw it from scratch the way I'm about to train you to do so. But if you can draw it from scratch, then you can answer any question about it. I do want to point out this little blurb on this slide, though, because I'm going to be referring back to it soon. That's a new little fact that you need to know, but we'll cover it in our drawing. So I'm sure that while you are copying down these slides, you noticed, whoa, there are a lot of steps to drawing this. And you're right. The burden is on you to be able to draw them from scratch. You're not going to ever have these steps in front of you on an exam. But the good news is that it's kind of rational. It's not abstract the way the half reactions were, where you're like, oh, okay, now we're adding water. All right, these, if you understand what's happening in the Voltaic cell, then there's kind of a flow to what's going to have to go where. So I'm going to go through all 16 steps with you, and we'll draw two Voltaic cells together. Are you ready? So here's the reaction that I'm going to be referring to for the first 16-step process. So make sure that you are looking at this redox reaction between cobalt and copper 2. And let's show what would happen in the Voltaic cell between them to make it work. Starting with step 1, here we go. Step 1 says, draw the half cells. Okay, well what that means is we're going to have inside our system these two half cells where different reactions are taking place. It also says that in those two half cells there needs to be liquids and solids. So there's our start. Step 2 says connect the solids together by a wire. All right, so here's my wire. Connecting the solids to one another. The wire is going to ultimately be the pathway by which electrons will flow from one half cell to the other. Because since redox is what's driving these electrochemical reactions, of course, it's electrons moving around that is going to be a big focus of ours. Step 3. Assign an identity to each solid. So here's my two solid pieces. And if you look in the equation, there's also two solid items. So just name them. I'm going to name the first one over here copper. And I'm going to name this one cobalt. Doesn't matter which is which, all right? And if you do them separate, then your picture is going to be the opposite of mine. But it doesn't matter which solid you give each solid. Step 4. Assign each liquid an ion identity that matches the solid. Again, look at the equation, and you'll see that we're pulling from the equation. All right, but I see for copper that we've got copper 2, and I see for cobalt that it's cobalt 2. That's the ion floating in the solution. Step 5, our battery is going to be standard. We learned on Monday that the standard concentration is 1 mole. Step 6, write the half reaction of each cell. Now this skill comes from Monday, but it's real simple. This is an easier one than some of the more difficult ones that we practiced. But if you look at the redox reaction, we can go through just really a couple, because we get to skip most of our half reaction steps here. Watch. The first cell here with copper is going to use copper 2 yielding copper. All right, and I pulled that right from the equation. You can see that in the equation, copper 2 is a reactant and copper is a product. And when we do half reactions, we connect the two things in common. All right, the other half reaction, we've got cobalt as, this is my cobalt cell. So we've got cobalt as a reactant and cobalt 2 as a product. We need to balance the half reactions though, and you could go through all 7 of those steps, but most of them get skipped, all right? Because we can't, it's 1-to-1 and 1-to-1, so there's no balancing. The oxygens are fine, the hydrogens are fine, it's only the charge that's wrong, all right? So I can easily fix the charge, all right? 0 charge, so let's make there be 0 charge over here. 0 charge, so let's make there be 0 charge over here. And now we've got balanced half reactions. You're welcome to interrupt me if anything confuses you, of course. Let's move on to step 7. It says label reduction and oxidation. We've already learned this as well. Remember, if electrons are reactants, that's automatically reduction. If electrons are products, that's automatically oxidation. Step 8, label the cathode and the anode. Now here's where things are slightly different in terms of vocab, all right? These items that are actually connecting our two half cells are called electrodes, all right? And electrodes are either going to be a cathode or an anode, and it simply depends on which direction the electrons are traveling to determine who's the cathode and who's the anode. Now, if you go back to slide 2 of the lecture, there was a blurb there that I mentioned would be important at this point. The way that I remember it is that the vowels line up. Whichever side is being oxidized is the side that's the anode. Both of them start with a vowel. Therefore, reduction happens at the cathode. We can label the signs on our battery. All right, hey, look at cat and Ann, right? So you probably already can see that this is positive and this is negative on the battery label. Step 10. Show electrons flowing from anode to cathode via the wire. That is the pathway of the electrodes, will always be from the anode to the cathode. All right, so my anode's on this side, so I'm going to use arrows to show that my electrons are traveling that way through the wire. If you're asked to do this in an FRQ, make sure you show the electrons near the wire. Several years ago during an FRQ, we AP teachers received a notice that students were losing points on this FRQ question because these arrows, they were drawing it straight through like this. For the most part, the students weren't thinking that the electrons were going through the half cells directly. They were showing correctly that they were traveling from anode to cathode, but they just weren't being specific enough in their drawing, and they were losing points. So careful, the electrons are going to travel through the wire that's connecting the two half cells. Number 11. Since electrons are always traveling from anode to cathode, we can predict a change in size of both electrodes. Over the course of the reaction, the cathode that is receiving particles is going to be growing. Whereas the anode that is losing particles is going to be shrinking. Another real important thing, especially for us in the lab setting, is going to be color changes in the half cells. Because if you set up this apparatus, the very first thing you'll be able to notice as the reaction progresses is color changes in each half cell. If you look on the very last slide of your notes, you'll see that I provided you with common colors of some ions in solution. It's very important that you know those colors, like actually know them for the exam, the AP exam. Because you might be asked to denote what color changes, it's a very common FRQ question, you would expect during the Voltaic cell reaction. For example, Cobalt is listed as pink on your sheet there, all right? So let's talk about what's going to happen. Now remember, the colors are the ions. The color is going to reflect the amount of ion that's present. Okay, well, what's happening in the reaction? Copper here is losing electrons. If copper loses electrons, he is left positive. Therefore, during the reaction, my solid here is depositing more CO2 plus into the half cell, right? Because if you're pulling electrons away from cobalt, it's going to become a positive cobalt. Therefore, there are more ions being formed there. So the color is going to be pinker. Well, what about over here? Well, copper is listed as, copper ion is listed as being generally bluish, all right? Well, if electrons are being distributed to this cell, it's adding negatives to the copper too. So really, it's going to be sitting there reducing it. We knew that. And it's going to be making it become copper. Therefore, less ion is going to be present in the cathode, all right? Because the electrons are getting rid of the ion. So what would we expect that color to be? I'm going to call it less blue. Because we're losing the color there. To my last section of steps. Here's the chemical problem with our setup right now. Initially, the reaction is going to send one electron from one half cell to the other, and it will produce some energy, some volts. However, once that first electron gets there, we have a charge buildup that's going to stop the reaction. Think about it. The moment we send a negative over there, and this system has kind of a more negative feel to it, why would more electrons want to go? I mean, not only would more electrons be traveling towards a negative environment, which they hate, electrons hate negative, but this environment is slightly more positive than it was before the first electron traveled, making these electrons that are still here have a better reason to stay. So we've got double whammies preventing a second electron from traveling and continuing the reaction. So after one electron goes, the reaction's going to just stop and the battery's going to die. But there's something else there to fix this problem. Number 13 in your steps says add a salt bridge. And here's what a salt bridge looks like. There's my salt bridge. And inside that salt bridge is going to be a compound that's going to release this charge buildup. It's going to solve our problem of the negative and positive environments being built up and blocking electron movement. You'll notice that step 14 says that the substance you should include in your salt bridge should be a group 1 nitrate. The reason that you need to do that is because the salt bridge is going to be seeping ions into your half cells. And if you seep in ions that can form precipitates, it's going to start doing other reactions. But nitrates, as we learned in Unit 2, they're always soluble, always. So use an alkali metal nitrate, and you'll never have to worry about a precipitate throwing off the reaction from a different angle. So name an alkali metal. Lithium. Let's do lithium nitrate in our salt bridge. So I'm going to put lithium nitrate in that salt bridge. Step 15 says the salt bridge will solve our issue by sending the positive ion to the cathode, which in this case is lithium, and the negative ion to the anode, which in this case is nitrate. And think about what that does. Every time an electron comes over here and makes this half cell slightly negative, the salt bridge feeds over a positive ion to get rid of the charge buildup. Or you could say every time an electron leaves this half cell, leaving it slightly positive, the salt bridge seeps in a negative ion, gets rid of the charge buildup, and now more electrons can travel again and again and again, and the electrochemical reaction will continue. The last thing I want to show you is how to write this in shorthand. Understand that all you need is the half reactions to write shorthand, but what's nice is that if I wanted to describe this Voltaic cell that I built, I wouldn't necessarily have to show another scientist all this work. I could just show them in shorthand notation what the half reactions are, and they could come up with the drawing. This abbreviation is very simple, all right? As step 16 says, you're always going to do the anode, then the cathode, so it's in alphabetical order, all right? And you just write all the non-electron information that you see in the half reaction. So let's start with the anode, all right? So first I see cobalt, all right? So I'm going to go cobalt and draw one line. Next on the anode, I see cobalt 2. Cobalt 2, I'm going to draw 2 lines because I'm done with the anode. Over on the cathode, the first non-electron thing I see is copper 2. Draw 1 line. And then I see copper. And there is your shorthand notation. How are we doing? A lot of steps, but I don't think any individual step is extra hard. Want to draw another one with me? Oh, you shake your head no? Let's go again. He is a brilliant mind. Now, this other cell that we're going to draw does start off a little bit meaner than the first one did, because as you look at our new problem, you'll notice that it's not giving a reaction. It's just saying that redox is going to happen. And it's with copper in a species and iron in a species. But you don't know what the redox reaction looks like. Now, let's talk about this. Remember how it works, all right? If I know that two items are going to form a redox, but I don't know who's going to be reduced or who's going to be oxidized, then I have a tricky little friend I can use to figure it out. My table. All you have to do to figure out the half reactions here is write both reactions as reduction. Write both of them with electrons as reactants. And you'll be able to find them both after you do that on your chart. Which one will be reduced? Whichever one has the higher cell potential, E, on the chart. So let's write both reactions as reduction. Whoever's got the highest number can stay reduction, and the other one will just become oxidation. Now, I've already done it on the hidden board, so this part's going to go kind of fast, but follow my thought process. So what I did was I wrote initially copper as reduction and iron as reduction, all right, based on what's given at the beginning of the problem. And then I went and looked them up on your table. You can verify your table has them at 0.34 and at negative 0.036. The smaller number lost the battle. The smaller number isn't going to be the one reduced. So I kept the larger number as is, and I flipped the other reaction. By flipping the iron reaction, it becomes oxidation, all right? And I got to flip the sign of the cell potential, and now I'm ready to move forward. Now, I did something here that you don't have to do. I found the overall cell potential of the system. It didn't ask us to do that, but remember, you just add the numbers together to do that. And I did prove that it's thermodynamically favored because E is positive. So here's the half reactions that will ultimately describe the voltaic cell we're about to draw. You ready? It'll go faster this time. I do hope you'll interrupt me if you need to. Step one, draw some half cells with liquids and solids. Draw some half cells with liquids and solids. Step 2, connect the solids with a wire. Step 3, identify the solids from the equation. So look back at what we're dealing with, all right? And I am going to name the first one iron and the second one copper. Step 4. Attach the liquid identity to the solid identity, still using the equation. In this case, I'm going to have iron plus 3 and copper plus 2. Step 5, make the solution standard. Step 6, write the half reactions, which we already found the exact half reactions, so just put them in the proper spot. All right, so we're going to have iron going to iron 3. And then we're going to have copper 2 going down to copper. Step 7, label reduction and oxidation. Electrons as products is oxidation. Electrons as reactants is reduction. Label the cathode and the anode. Oxidation always takes place at the anode. Look at the vowels. Reductions at the cathode. Label the label the charges. Anode negative, cathode positive. Electrons will flow from anode to cathode through the wire. Let's show that. The anode is always going to be shrinking. All right. Well, the cathode is growing. I'm going to label the color changes here. I know that my iron is losing electrons. If it's losing electrons, that means that we're going to be depositing more positivity here, more cations. Therefore, the color of the iron will become more vibrant. So I'm going to call this redder. I know that the copper is gaining negatives, therefore this positive is going to be turning into solid copper, which is another reason the cathode is growing. We're actually depositing more and more metal onto the cathode, all right? This is a way that we can actually plate jewelry, is through this process. But anyhow, it's going to be taking ions out of the solution, so it's going to be less blue. We have a charge buildup. We don't want the reaction to stop after an electron moves, so let's add a salt bridge. Get our salt bridge ready. There she is. All right. Let's put an alkali metal nitrate into the salt bridge. I'm going to choose sodium nitrate is a good choice. He won't form a precipitate with anybody. And I know that my salt bridge is always going to deposit a negative ion towards the anode and a positive ion towards the cathode. Now the electrons that are trying to make the solution, the half cell negative, will be counteracted. The negatives that are leaving, trying to use the half cell, leave the half cell positive, will be counteracted. And hooray, hooray, the electrochemical reaction will continue to take place. My shorthand is going to always go anode to cathode alphabetically. So I see iron, followed by iron 3, followed by copper 2, followed by copper. Questions over galvanic cells?